Imagine you have a leak under your kitchen sink.
Oh, the worst.
Right. Water is just spraying everywhere. It is a total panic mode situation. So you grab a massive, tangled roll of heavy-duty duct tape, and you just start wrapping the pipe.
Just going to town on it?
Exactly.
Yeah.
You apply layer after layer, overlapping, crisscrossing, creating this massive, chaotic bulge around the metal. And miraculously, the leaking actually stops. It works.
Phew.
The immediate crisis is solved, and you walk away feeling totally victorious.
Well, yeah, until a few days later, right? When a professional plumber comes over to do some routine maintenance.
Oh, no.
Yeah, they open the cabinet, take one look at that sticky, gray, baseball-sized knot of tape on the pipe, and just sigh. I mean, the crisis was averted, sure, but the plumbing itself has become a completely unreadable mess.
Nobody looking at that massive ball of tape can actually understand the underlying pipe structure anymore. If a new leak springs up right next to it, the next person has absolutely no idea how to navigate around your fix. Like, the water isn't dripping on the floor, but structurally, it is a nightmare.
It perfectly illustrates the classic divide between getting a job done and making that job understandable for the future. You know, building something that functions is a completely different skill set from building something that communicates its function.
And that fundamental tension is exactly what we are exploring in today's deep dive. Welcome, everyone.
Glad to be here.
Today's mission takes us into a highly specific technical artifact, but the underlying psychology. It applies to just about everything we do. We are examining a blog post published today, June 23, 2026.
Hot off the presses.
Right. It is titled, Notes on Haskell Programming, Part 168, Refactoring for Clarity. And it comes to us from a developer named Ang.
So just to clarify for everyone, the subject matter here is code, specifically written in a functional programming language called Haskell. We are looking at the delicate and honestly, often deeply frustrating art of refactoring.
Right, and for anyone who might not use that term daily, refactoring basically means rewriting and restructuring existing code to improve its readability and maintainability.
Right, but without changing its external behavior.
Exactly. You aren't adding new features. You are just cleaning up the plumbing.
And look, even if you are listening to this right now with zero technical expertise, even if you have literally never heard the word Haskell before, this deep dive is going to resonate with you.
Oh, 100%. Because we are fundamentally looking at the battle between finishing a task and making that task comprehensible. I mean, you experience this tension all the time.
Right, like when you are organizing a massive, unwieldy spreadsheet.
Yes. Or when you are drafting a complicated multi-thread email to your team, or when you are trying to establish a new workflow. You throw something together to meet a deadline, and then you have to decide, am I going to leave it as a mess or refine it into something elegant?
And that tension is exactly what makes this coast from Ang so compelling. It acts as a window into the psychology of structuring information. We are looking at how to arrange logic so that a human brain, with all its limitations in working memory, can actually process it without becoming totally exhausted.
So let's set the scene and figure out exactly what Ang was dealing with before this whole refactoring effort began. In a previous post, Ang had tackled a very specific bug, a string replacement issue.
Right.
Ang wrote the code, deployed it, and successfully fixed the problem. The duct tape stopped the leak.
It did. The solution worked flawlessly from the machine's perspective. The string replacement issue was entirely resolved. I mean, the computer was happy to execute the commands.
But Ang was dissatisfied.
Highly dissatisfied. The generated code was, in Ang's own words, not readable for my taste.
Okay, let's unpack this. Ang had a problem, wrote code that solved the problem, and the machine executed it perfectly. If fixing the leaky pipe with duct tape stops the leak, why isn't it enough that the code just fixes the issue?
That is the big question.
Right. I find it fascinating that a developer uses a word like taste when discussing machine instructions. Why does code need to cater to human aesthetic preference at all?
Well, this raises an important question about who we are actually writing code for. There is this persistent misconception that code is just a set of instructions for a computer.
Sure, that's what most people think.
But the reality of software engineering is that code is read by human beings far more often than it is written. A computer will happily compile a tangled ball of logic. It has infinite patience.
Flawless memory, too.
Exactly.
Yeah.
Human developers do not. The human who have to look at that code next, which is, by the way, very often the original author just 6 months later, has to rebuild the entire mental model of what that code is doing.
Oh, wow. So the taste Ang is referring to isn't just about making it look pretty on the screen. It is about cognitive load.
Yes, precisely.
When you write something that is mathematically dense but incredibly chaotic, you are forcing the next reader to burn an immense amount of mental energy just trying to decipher your intentions before they can even begin to do their own work.
And Eng's dissatisfaction is proof that having working code is really only step one. The actual finish line of professional development is readable code. And this is especially true in a language like Haskell.
Right, Haskell is purely functional.
It is a purely functional programming language, yes. It is famous for allowing developers to write incredibly concise, mathematically pure logic. But, that conciseness can be a double-edged sword. If you aren't careful, a dense block of Haskell can look like alien hieroglyphics.
It sounds like writing a brilliant, Pulitzer-worthy novel, but deciding to remove all the punctuation and paragraph breaks just to save paper.
That is a great way to put it.
I mean, the words are all there, the plot happens, and the machine can print the book. But the human being trying to read it is going to experience a massive headache by page 3.
Absolutely. Recognizing this, Eng decided to embark on a process to untangle the logic. The source material notes that Eng went through several rounds of refactoring. The primary goal was to ensure that the main logic remained lean and focused within the function body.
So what does this all mean? Let's look at the actual mechanics of how Eng achieved that. We're moving into the first phase of the solution, which we can call the structural shift. This is all about flattening the logic.
Right, to get that lean function body, Eng had to physically restructure the code on the page, completely separating the main goal from the background noise.
How exactly?
Mechanically, Eng moved away from using deeply nested let-in blocks.
Let-in blocks.
Yeah, in Haskell, a let-in block is a way to bind a variable or define a local function right in the exact spot you're about to evaluate it. You basically say let x equal 5, let y equal 10 in x plus y.
Oh, I see. And when you start heavily nesting those inside each other, you are forcing the human brain to act like a computer's short-term memory. You are asking the reader to hold variable A in their head while they read variable B, which is dependent on variable C.
It's exhausting. The source notes that Eng deliberately removed these hidden intermediate variables because they were just cluttering the main stage.
Let me put this into a slightly more everyday context to explain why that structural shift is so vital. Imagine you are reading a recipe for baking a complex cake.
Okay, I'm with you.
You're reading straight down the page, and you arrive at step 3, which tells you to mix the batter. But right in the middle of that sentence, the recipe abruptly launches into a heavily nested, 5-page, highly technical detour explaining the metallurgical process for mining iron ore, smelting it, and forging the specific metal mixing bowl you were supposed to be using.
Oh my gosh, you would lose your place instantly.
Completely lost.
By the time you finished reading about the smelting process, you would have completely forgotten that you were even trying to bake a cake.
Right. That is the exact cognitive experience of a deeply nested let-in block. It is logic hidden inside of logic. It interrupts the main narrative just to define the tools.
And Eng realized this structural nesting was muddying the waters. The solution was to take all of those background definitions and relocate them down into a where block.
Okay, what is a where block?
A where block in Haskell allows you to append your definitions at the end of the function. So you state your main logic first, and then you say, oh, by the way, where variable x is this, and where helper function y does that.
So sticking with the recipe concept, moving things to a where block is like taking all that intense prep work and all the tool definitions and putting them in an appendix at the absolute bottom of the cake.
Exactly.
The main recipe, the function body, stays incredibly lean. It just reads, mix the batter in the bowl. If you, the reader, trust that the bowl exists, you can just keep baking.
Yes.
And if you really need to know the specific details of how that bowl was forged, you can always glance down at the where block at the bottom to investigate.
Right, and the code reads cleanly from top to bottom. Eng explicitly points out the value of removing those hidden intermediate variables. When variables are hidden deep inside nested blocks, things are happening off stage. It forces the developer to hold secret, invisible values in their working memory.
Which we know is a bad idea.
Right. By moving them to a clear where block, Eng brought immense transparency to the entire process.
I also really want to highlight the timeline here. Eng notes this took several rounds of refactoring.
It wasn't instant.
No. And it is a great reminder that clarity is an iterative process. You pull off the first layer of duct tape, and you realize the pipe underneath is still coated in sticky residue. You have to clean that off, too.
It takes work. So with the structural noise cleared away, Eng's post transitions into the actual mechanical tools used to process the string replacement data. We are moving from the physical layout of a code on the screen to the execution of the logic itself.
Okay, this brings us to the mechanical shift. The source material explains that Ang moved to using multiple fold L prime calls to handle the data processing.
Right, for those who aren't swimming in Haskell syntax every day, the post explicitly notes that a fold is effectively a for loop.
Okay, a loop.
Yeah, a loop in programming is a mechanism for repeating a specific action over and over again, usually across a set of data. In functional programming, a fold takes a list of items and literally folds them up into a single accumulated result by applying a function to each item one by one.
Got it.
Ang utilized these loops by leveraging the helper functions that had just been neatly tucked away in the where block we just talked about.
Okay, I have to push back on this approach for a moment.
Oh.
Yeah, if a fold is essentially a loop that iterates over data, why would Ang use multiple calls? If the goal of refactoring is to clean things up and make the code efficient, wouldn't the standard engineering approach be to consolidate everything into one massive, highly optimized loop?
That's the traditional thinking, yeah.
Right. If you break a single complex string replacement process into several distinct loops, you are running through the data multiple times. Are we sacrificing actual machine performance just to make the code easier for a human to read?
What's fascinating here is you have hit on the exact trade-off that defines modern software engineering. Ang is absolutely, intentionally trading clever, hyper-condensed logic for clear sequential steps.
Interesting.
In the past, programmers were obsessed with doing as much as humanly possible inside a single loop to save compute cycles. But when you try to do 5 different string manipulation tasks inside a single iteration, the logic becomes incredibly brittle. It is clever, sure, but it is unreadable.
It becomes a performance trick. Like, it is the difference between a single frantic chef trying to chop the vegetables, sear the steak, and plate the dessert all at the exact same time versus establishing a clear assembly line.
Exactly.
The single chef might technically get the meal out 3 seconds faster, but the kitchen is a war zone and nobody else can step in to help. On an assembly line, one person chops, the next person sears, the next person plates.
And that assembly line is exactly what Ang built with multiple fold L prime calls.
Right.
By chaining multiple folds together and having each one use a dedicated helper function from the where block, the code transforms into a traceable path.
A step-by-step process.
Right. Loop 1 walks through the data and does task A. It hands the result to loop 2, which walks through and does task B.
So you aren't guessing what the code is doing at any given millisecond. The state of the data is completely predictable at each station of the assembly line.
Yes.
The machine might have to work a tiny fraction harder to loop twice, but the human saves hours of debugging time.
Which brings us to the final and arguably most profound change detailed in the post. Once the structure was flattened and the mechanics were broken into clear assembly line steps, Ang executed a linguistic shift.
Here's where it gets really interesting.
Yeah.
Because we are moving away from math and moving into language, the title of Ang's blog post is Improving Code Clarity with Semantic Functions. The word semantic is the key.
The source states that Ang completely removed what are called inline lambdas and replaced them with named local functions.
Inline lambdas.
Yes. To understand why that matters, we have to define what an inline lambda even is. In programming, a lambda is an anonymous function. It is a raw, throwaway block of logic that you write directly in the middle of your code without ever giving it a formal name.
So you just type the mathematical operations right there on the spot.
You do. You are telling the machine exactly what calculations to perform, but you are not assigning any human identity to that calculation whatsoever.
Let's contrast the aesthetic vibe of a mathematical inline lambda with the specific semantic names Ang chose to implement. The post gives us 2 concrete examples of the new named functions: hide keyword and swap keyword.
Great examples.
Think about the psychological difference there. An inline lambda feels like a cold, anonymous equation. It is just algebraic symbols shifting memory around. But hide keyword, swap keyword, those are verbs. They have intent.
They absolutely do.
By giving a block of logic a semantic name, you are giving it a human identity.
It completely shifts the focus of the code. I mean, semantic means relating to meaning in language or logic. When you use an anonymous inline lambda, your code is obsessed with the how. It tells the computer how to manipulate the bytes of the string. But when you wrap that exact same logic in a function and actually name it hide keyword, you're explaining the what.
The what?
Yes, you're telling the future human reader what that string is actually experiencing in the real world.
You are stepping out of the role of a calculator and stepping into the role of a storyteller.
You absolutely are. You are looking at the assembly line and saying, at this specific station, We don't just manipulate variables, we hide the keywords. And at the next station, we swap the keywords.
Wow.
Ang explicitly notes that providing these meaningful semantic names drastically improve the readability of the entire file. It bridges the massive gap between raw machine execution and human comprehension.
It is the exact same psychology we use when organizing files on a personal computer. I mean, you could theoretically have a folder full of PDFs named Document 1, Document 2, and Document 3.
Oh, I've seen desktops like that.
Right, and the operating system doesn't care. It stores them flawlessly. The file system works. But if you try to find your tax return from 2 years ago, you are completely lost in a sea of numbers.
Totally lost.
But when you take the time to rename those files to 2024 taxes or car insurance policy, you are performing a semantic shift. You are looking at a block of digital data and assigning it a real-world, domain-driven identity.
And that process requires genuine effort. It demands that a developer actually stop typing, look at a block of anonymous logic, and ask, what is the true essence of this operation?
Right.
Distilling complex math into a clear, concise two-word name like swap keyword is an act of translation. You are translating machine state into human intent.
Which beautifully sets up the final leg of our journey through Ang's Part 168 post. We have examined the structural shift of moving definitions to the bottom. We have seen the mechanical shift of breaking complex loops into simple sequential steps. We have analyzed the linguistic shift of using semantic names. Now we arrive at the reality of being a pragmatic creator.
Yeah, this is the best part.
The post moves from a technical triumph to a surprisingly grounded realization about the limits of perfectionism.
Right. After detailing all of these incredibly elegant changes, Ang pauses in the text and asks a rhetorical question. Are there ways to improve this?
And given how much work was just put into this refactoring, you almost expect Ang to say, no, this is now a flawless masterpiece of functional programming.
Right, but Ang's actual answer is incredibly telling. The post says, probably, but so far, this is probably the best we can refactor now.
I love that honesty.
If we connect this to the bigger picture, that single sentence reveals profound pragmatic wisdom. Ang clearly understands the engineering concept of diminishing returns.
So true. The initial problem was that the code worked, but reading it felt like untangling duct tape. That was a high-friction problem actively hurting productivity, so it was worth the investment of time to solve.
And Ang invested that time. The logic is now lean. The loops are traceable. The names are highly semantic and actually tell a story. Could a world-class Haskell developer find a way to make it 5% more efficient? Probably.
Yeah.
Could someone brainstorm a function name that is 2% more descriptive?
Yeah.
Almost certainly. But Ang recognizes that chasing that final microscopic margin of absolute perfection simply isn't worth the mental energy.
It is a phenomenal lesson in knowing when to step back from the canvas. Whether you are agonizing over the precise phrasing of a single bullet point on slide 40 of a massive presentation, or you are endlessly reorganizing the tools in your garage, at some point you have to look at the work and say, this is probably the best I can refactor right now.
Yep.
Perfect becomes the enemy of the good, and more importantly, the enemy of the finished.
It is the hallmark of a mature professional. You recognize when the duct tape has been removed, the structural integrity of the pipe is restored, the water is flowing clearly, and it is time to just close the cabinet doors. Ang's sign-off at the very end of the post reflects this perfectly. It just says, till the next post, yours truly, Ang. There will always be another post. There will always be another piece of code to write. You cannot get paralyzed trying to endlessly polish the current one.
Well said.
Mm.
To quickly summarize our journey through Ang's notes today, we started with a leaky pipe that had been hastily fixed. We discovered that simply resolving a string replacement issue wasn't enough because in software, the human reader matters just as much as the machine compiler.
Right.
By systematically moving away from heavy, nested lead-in blocks and appending definitions to clean where blocks, Ang flattened the cognitive load.
Huge structural shift.
By breaking complex data processing into clear, sequential fold-L loops, the mechanics became an easy-to-follow assembly line. And most importantly, by throwing away anonymous lambdas and embracing semantic intentional actions like hide keyword, Ang transformed cold logic into a human-readable narrative.
The refactoring process turned an artifact built for a computer into an artifact built for a human. But as we wrap up this deep dive, I want to leave you with a final thought to explore on your own.
Okay.
We've spent this entire time talking about refactoring code, but I want you to consider the inline lambdas in your own daily life.
Oh, I love that framing.
Think about the complex, chaotic, unnamed routines you execute every single morning just to get out the door.
So many of them.
You probably have an incredibly dense, nested loop of habits that you just blindly execute to keep things running. If you took 10 minutes tomorrow to step back, to physically structure your morning differently and to give those chaotic routines clear semantic names based on their true purpose,
Wow.
would it change the way you understand your own behavior? If you stop referring to it as just surviving the morning and name that block of time, prepare for, focus, or nurture the family, how would that linguistic shift alter your relationship to your own daily grind? Untangle your own duct tape. Give your actions a meaningful name.